Okay, so we're doing chapter 9, problem 21 here. So we have this 224 kilogram projectile, and it was fired with a speed of 116 millimeters per second at an angle 60 degrees with the vertical or horizontal. And it breaks into three pieces of equal mass. So we have this into three pieces of 1/3 mass each. Two of the fragments moved with the same speed right after the explosion as the entire projectile had just before the explosion. One of these moves vertically downward and the other horizontally. And we want to determine the velocity of the third fragment. Okay, so for the initial projectile motion, we should know that the horizontal velocity in the x direction is constant, because the only force acting is just gravity, and that's all in the y direction. So the velocity at the highest point, right when the explosion happens, is the entire velocity. It's all horizontal at that point. So that means the entire velocity there is just Vx equals the initial speed times cos theta, because that's just the x component of the initial velocity, and the initial velocity and the horizontal component stays constant. So we know that the momentum before and after the explosion needs to be conserved. So we know that P before equals P after. Okay? So if we let V3 be the velocity of the third fragment, this is what we're trying to find. Okay? So let's start writing out our momentum equation. So initially, we know right before we are only moving horizontally with this as our speed. So the momentum at that point is given as P before, and this is m v naught cos theta, and this is in the x direction of momentum, so this is in the I hat direction. So this is our P before. So now let's start writing out what our P after is. So we have one fragment says moving at the same speed with 1/3 mass. So that's 1/3 mass, times v naught times cos theta. And we have two of these. It says two of the projectiles are moving with the same speed, but one's moving horizontally and one's moving vertically downward. So for the horizontal one, this is in the I-th direction. And now we can add another one with the same mass and speed. But they said this is moving vertically downward, so that's in the negative j hat direction. So this is two of our three components, and our last one is just 1/3 mass times whatever this v3 velocity vector is. So now that we have this equation, we can just solve for what v3 is. So if we rearrange things and solve for v3, we get 2v naught cos theta. This is in the I hat direction. And we have v naught cos theta in the j hat direction. Cool. So now we can plug stuff in and figure out what this is. So this is 2 times 116 meters per second times cos 60 degrees in the I hat, plus 116 meters per second times cos of 60 degrees in the j hat direction. Awesome. If we plug all that in, we get our velocity vector of the third component as 116 meters per second I hat plus 58 meters per second j hat. Cool. So there is our velocity vector of the third fragment. So that was part A. So now for part B, it is asking what is the energy released. Okay, so the energy released is just going to be the difference in kinetic energies. So I'm going to add this new page here. So the energy released is going to be the difference in the final minus the initial kinetic energies. So this is K before, or K after minus K before. So this is going to be a lot of stuff, but we can just calculate this. So let's first do K after here. So this is 1/2 times 1/3 m v naught cos theta squared. Okay, so that's one of them, and we have two of these because two of them are moving at exactly the same speed and mass, so we can just multiply that by a 2. Now we can add the third one, which is 1/2. Oops, sorry, not 1/2 m. 1/3 times 1/2 m v3 squared. So this is our k after, and we can subtract off the k before, which was just 1/2 m v naught cos theta squared. Awesome. So what we can do is now simplify some stuff here. So if we simplify this out, we should see we can pull out a 1/2 m here, and we're left with 2/3 v naught cos theta squared minus v naught cos theta squared plus 1/3 v3 squared. Okay, so if we plug all that in, we can plug in what we got for v3, because the magnitude of v3 squared is given from our part A answer as 2 v naught cos theta squared plus v naught cos theta squared. So let's plug that in and simplify, and we see this comes out to something pretty simple. And this is just 2/3 m v naught squared cos theta squared. Cool. So let's plug this in. 2/3 times 224 kilograms times 116 meters per second squared times cos of 60 degrees squared. Awesome. And finally, we can get our amount of energy released in the explosion, and it comes out to being 5.02 times 10 to the 5th joules. Awesome.